And we're live. Hello and welcome. This is going to be our homework help video for the very lengthy 14-1 Trig Identities homework. Give you guys a couple days to get this one done. So really I'm hoping to see good quality work. Your work should be done on a scratch piece of paper and stapled to this, just because there's not enough room to really verify each of these and give the domain of validity. So I've got a copy of it in front of me. I also have my purple packet with all of the identities. You're going to need both of those, and I'm going to be showing my work on just a blank sheet here so that I can have plenty of space to write. We'll just start with number 1. Might as well. This is the identity sine theta, secant theta, cotangent theta equals 1. I'm going to start by verifying this. The first step in verifying is, well, let me start with my goal in verifying is to get the left-hand side equal to the right-hand side so that I know for sure this is a true statement. The first step in doing that is to do something called decomposing into sine and cosine. It's possible to start with any trig function and take it into sine and cosine. Let me just write up those identities real quick. These are some of the very first ones. Sine and cosine, obviously, we just leave those alone. Tangent, I'm going to use a quotient identity to rewrite this as sine over cosine. Cosecant is 1 over sine, secant is 1 over cosine, and cotangent is cosine over sine. So notice this is everything in the right-hand column over here is just in terms of sine and cosine. So this is how to decompose all functions into sine/cosine. All right, so sine stays sine. Switch to blue here. Sine is going to stay sine. I'm going to stop writing the thetas for a little bit until I'm ready to write my final answer. Secant, that's 1 over cosine. Cotangent, that is cosine over sine. And we'll just leave the 1 alone. When we use an identity, let's just use a letter code to let us know what we're doing. If we use a quotient identity, we're going to use a Q. If we use a reciprocal identity, we're going to use an R just to show our work. So this was a reciprocal identity here. This is a quotient identity, so we're going to put a Q there. All right, if I've got a function in front of a fraction, I can bring that on top of the function. Now I've got sine over cosine times cosine over sine equals 1. The sine will cross-cancel with the sine. The cosine will cross-cancel with the cosine. Still something is left behind. A 1 is left behind. That's because, in effect, sine divided by sine is 1. Cosine divided by cosine is 1. 1 times 1 is just 1. When we cancel, a 0 isn't left behind. A 1 is left behind. It's something important to note. I've got the left-hand side equal to the right-hand side, so I can draw my box. This has been verified. Now I've got to state the domain of validity that this identity is true for. To do that, above each, I write the ratio that it represents. Sine is opposite over hypotenuse. Secant is hypotenuse over adjacent. And cotangent is adjacent over opposite. It might be worthwhile to just quickly write those down. So you don't have to just like always be thinking about it. You can just maybe refer to a list of these. Halfway done. Cosecant, hypotenuse over opposite. Secant, hypotenuse over adjacent. Cotangent, adjacent over opposite. All right, then I look at specifically the denominators, adjacent and opposite. If I have both types, then it's x cannot equal n pi over 2. And somewhere at the very top, write that n is an element of the integers, and that'll be valid for the whole paper. Let's just take real quick notes on those excluded values. If I have just opposites, it's going to be n pi. If I have just adjacents in the denominators, it's going to be, this is the tricky one, n plus 1/2 pi. And if I have opposites and adjacents, it's n pi over 2. Specifically, x cannot equal those. All right, so there's a bunch of notes that'll kind of help you through this. Now we can start going a little bit quicker with number 2. Cosecant equals cotangent secant. I'm just not going to write the thetas till the very end. Not super necessary. This is number 2. Did I write a number 1 up here? Yeah, we'll circle that. Okay. Decompose. Cosecant becomes 1 over sine. Cotangent becomes cosine over sine. That was a quotient identity. That was a reciprocal identity. Secant, we'll use another reciprocal identity to rewrite that as 1 over cosine. Cosines cancel. 1 over sine equals 1 over sine. Left equals the right. We write our box. Let's copy in the correct ratios now. So we got hypotenuse over opposite, adjacent over opposite, hypotenuse over adjacent. We got both types. So x cannot equal n pi over 2. And that's all the work needed for number 2. Number 3. This is a good one. Got a sine squared in it. So sine, I'll write the thetas this time. Sine theta cosecant theta equals sine squared theta. First step is still the same. We still want to decompose into sine and cosine, see what we can do. So now I've got sine over, make this fraction line a little bit bigger. Cosecant is 1 over sine equals sine squared. So that was, draw an arrow here, we used a reciprocal identity to rewrite cosecant as 1 over sine. Now we copy dot flop. To divide by a fraction, you copy the top, you write a dot to replace that, and you flip the bottom. So now it's just sine over 1 equals sine squared. That 1, dividing something by 1 doesn't change it. The sine gets multiplied by that sine. Now we've got sine squared. Now I can write the theta equals sine squared theta. Left equals the right, draw a box. Let's write down all of our ratios. We've got an opposite over hypotenuse. We've got a hypotenuse over opposite. We got an opposite over hypotenuse. Circle the denominators. Hypotenuse, hypotenuse, those don't matter. The opposite does matter. So x cannot equal n pi. Notice even though this is a big fraction, the denominators still matter, even if it's in the top of the fraction, the bottom of the fraction. It's just what are the denominators. For cosecant, I had an opposite. Opposite is equal to 0 at multiples of pi radians, or multiples of 180 degrees, if you like to do it that way. All right, let's see, 4 is awfully similar to number 1. I think we can skip that. 5 looks like we're going to have to add in our Pythagorean identity, so let's do number 5. Not positive, let's just see what happens. All right, how about blue? Here we go. Sine theta tangent theta plus cosine theta equals secant theta. Decompose, sine's going to stay sine. Tan is going to become sine over cosine, plus cosine's going to stay cosine. Secant using a reciprocal is going to become 1 over cosine. Now bring that on top of the fraction. Sine times sine becomes sine squared. Let's go to green. Plus cosine equals 1 over cosine. Two fractions on the left, one fraction on the right. I want it to be one fraction and one fraction. So I need to get a form of 1 or here. Well, I need to multiply by a form of 1. That will give me a common denominator so I can combine this into a single fraction. That form of 1 is I'm going to multiply just this term by cosine over cosine. This is equal to 1, so it's not something I have to do to every single term. I can multiply something by 1 without changing it. And when I do that, I'll get a common denominator. So after doing that, now I've got sine squared over cosine plus cosine squared over cosine equals 1 over cosine. Keep going. Now that I've got a common denominator, I can add their numerators. I get sine squared plus cosine squared over cosine equals 1 over cosine. And now, for the first time in this homework, we're getting to use the Pythagorean identity. Sine squared plus cosine squared is equal to 1. And now I've got 1 over cosine equals 1 over cosine. Draw your box. I should draw a P, or write the letter P on this line for our Pythagorean. The Pythagorean identity is cosine. Nope, let's start with sine. Pythagorean identity is sine squared theta plus cosine squared theta equals 1. And there's two others. They are in your packet. You can use them when they come up. We'll try to do one of those problems. All right, let's kind of scan through here. I'm going to try to pick one out that's going to use a different form of the Pythagorean identity. Sometimes it's kind of hard to tell. Let's see, that'll just become Pythagorean. Let's do number 9. Number 9 is actually pretty easy if you pick the right Pythagorean identity. Tangent squared theta plus 1 equals secant squared theta. This is one that I believe I had you basically do in class, where we just used the only Pythagorean identity that we know, but I'll let you use all of the Pythagorean identities in the packet. There is a Pythagorean identity that is tangent squared theta plus 1 equals secant squared theta. This is in the packet. So I'm going to use this to replace this here with secant squared theta. And now I've got secant squared theta equals secant squared theta. Just write a little p there to show that that's why you're able to do that. That proves that. Got opposite over adjacent. I've got hypotenuse over adjacent. Only adjacents in the denominator. That means that x cannot equal n plus 1/2 pi. I feel like we forgot to do domain of validity for number 5. We did. Let's just do this real quick. Opposite over hypotenuse. Opposite over adjacent. Adjacent over hypotenuse. Hypotenuse over adjacent. Only adjacents in the denominators. So x cannot equal n plus 1/2 pi. All right. Let's see. I'm going to try to pick a harder one. It's not too bad. Maybe number 15. 15 looks pretty good. sine plus cosine over sine plus, nope, not plus, equals 1 plus cotangent. All right, I think I'm going to focus mostly on the right-hand side this time. Step 1 is going to be to decompose into sine and cosine. So this side is all sines and cosines, so I'll leave it alone. This side over here, the cotangent can be written as cosine over sine. All right, that is a Q. Going to replace this 1 with a sine over sine so that I can get a common denominator. So the 1 here becomes a sine over sine. Those are equivalent, so it just replaces it. And now that they have a common denominator, I can add the numerators. And look at that. They are exactly the same. Amazing how that works out. Let's figure out the domain of validity. We got an opposite over hypotenuse. We got an adjacent over hypotenuse. We've got another opposite over hypotenuse. And we've got a cotangent adjacent over opposite. That's the only opposite or adjacent in denominator. So that means that x cannot equal n pi is the one for opposite. All right, hopefully you're getting a pretty good handle on these. Shall we do 16? 16 looks kind of tricky. Also, maybe 18. Try those out. So 16. For 16, cosine, quantity secant minus cosine equals sine squared. Start like how we always start, decomposing into sine and cosine. This is going to be cosine times 1 over cosine minus cosine equals sine squared. Now we're going to look for ways to maybe do some canceling. I can't really directly cancel anything, so I'll distribute this cosine in. When I multiply cosine to 1 over cosine, it'll become a cosine over cosine minus cosine squared equals sine squared. This here will become a 1 minus cosine squared equals sine squared. Few ways we can do this. One is to take my Pythagorean identity and manipulate it to match this, or rearrange this, and essentially if I add cosine squared to both sides, I will have the Pythagorean identity. I'm going to go with that first way because it's a little bit more tricky. And when doing verifications, you're going to avoid ever crossing the equal sign. Sometimes it can change things in a way that maybe you can verify something that's actually not an identity. There's a few ways that if you do the math right, you kind of play some math tricks, you can get an identity that's not really an identity. So I'm going to avoid crossing the equal sign. I'm going to do it this way. So I write down my Pythagorean identity. I'm going to subtract cosine squared from both sides. And now I've got sine squared equals 1 minus cosine squared. And so this is an equivalent identity to the Pythagorean identity, which we know is true. And so I can take this and use it as an identity. I can replace a 1 minus cosine squared with a sine squared because they are equal. This is just basic substitution. So this here can become a sine squared using that Pythagorean identity, as long as I show the scratch work for why that works. So that's why this works. Now I've got sine squared equals sine squared. I can write the thetas to make it a little bit more official. Draw my box. And now I've got adjacent over hypotenuse, hypotenuse over adjacent, adjacent over hypotenuse, opposite over hypotenuse. Only an adjacent in the denominator, so x cannot equal n plus 1/2 pi. That would give me all my odd multiples of pi over 2. All right, let's take a quick break, make sure this is recording. It appears to be recording. Said 18 looks like another good one. So on to 18. I will post all of these notes after I finish this video. 18, I've got a 1 minus sign, got a 1 plus sign, I've got a cosine squared. Don't really need to decompose into sine or cosine, so I'm just going to FOIL this. So first outside, inside, last. Multiply the first thing, so I'm going to get a 1. Outside, I'm going to get a plus sign. Inside, I'm going to get a minus sign. And last, I'll get a negative sine squared equals cosine squared. These will cancel, and I've got a 1 minus sine squared equals cosine squared. Let me start with my Pythagorean identity again. Over here is some scratch work. And this time, subtract sine squared from both sides. Now I've got cosine squared equals 1 minus sine squared. So now I can do a little substitution right here. Rewrite this as cosine squared theta equals cosine squared theta using a Pythagorean identity. That, and our domain of validity is just x equals all real numbers. This is the first time we've seen this. We don't have any sides that can be 0 from these. This is opposite over hypotenuse, opposite over hypotenuse, adjacent over hypotenuse. So nothing to exclude. This identity is true for all real numbers. You can plug in any angle and it will work. Very cool. All right. Moving on. We are past the part of the homework where we have to state domain of validity. That's nice. Simplify each trig expression. I'll do number 19. 1 minus secant squared theta. If you look at your identities, this is very similar to this identity over here, which states that tangent squared plus 1 equals secant squared. That's right in your identities. Pause the video and locate it now if you haven't already. Can I manipulate this to look like this? I can by subtracting a secant squared from both sides and subtracting a tangent squared from both sides. And now I've got 1 minus secant squared equals negative tangent squared. So I can now use a Pythagorean to simplify this into just negative tangent squared theta. And because this only has one term and this has two, we consider that to be a little bit more simplified. Let's try number 20. 20, I've got secant over tangent. This one, I'm going to want to use that decompose feature first. Make this 1 over cosine divided by sine over cosine. Copy dot flop this. So that was a reciprocal and a quotient identity. Copy the top, write a dot, flop the bottom. Cosines cancel out. I've got 1 over secant. This can be simplified using another reciprocal identity. 1 over secant is the same as cosine of theta. Locate that in your reciprocal identities. If you don't believe me, it's right there. 1 over secant is equal to cosine. And that's nice and simplified. It doesn't have a fraction. It doesn't have multiple terms. Moving on. More simplifications. Simplifications work just like those verifications, often decomposing into sine and cosine first, but occasionally looking for when you can just use a Pythagorean identity right away. Let's do, I guess, 22. Looks like a good one. I've got here secant cosine squared. This one I'm going to decompose first. 1 over cosine times cosine squared. This can hop on top of that fraction, so now I've got a cosine squared over cosine. A cosine cancels out with a cosine, and to show that I can just cancel out that little 2, and I'm left with cosine of theta. Final answer. 23. Cosecant squared minus cotangent squared. It's similar a little bit to number 11. Well, I've numbered my identities. It's number 11 on my sheet, but it's similar to a Pythagorean identity. I think I'm going to just go with that. So here's the identity straight off the sheet. 1 plus cotangent squared equals cosecant squared. If I just subtract a cotangent squared from both sides, I'll get that 1 equals exactly what we're seeing over there. So I can just, boom, this equals 1. Using a manipulated Pythagorean identity. All right. Trying to find a more tricky one. 26. Cosine, cotangent, plus sine. Decompose real quick. If you got cosine times cosine over sine plus sine. I can bring that cosine on top. Now I've got a cosine squared over sine plus sine. To get a common denominator, I'm going to multiply this sine by sine over sine. That's a form of 1, so it doesn't change anything, but it enables me to combine these. So now I've got cosine squared over sine plus sine squared over sine equals sine squared plus cosine squared over sine. Pythagorean identity on the top of that. I've got 1 over sine. 5 minutes. Okay, sounds good. All right. Here's a real tricky one, number 31. I don't know if it's really tricky, but it looks kind of longer. All right. Sine over cosecant plus cosine over secant. Decompose into sine or cosine to start. And I'll have sine over 1 over sine plus cosine over 1 over cosine. Copy dot flop both of these. So copy the top, multiply by the bottom flipped over, plus copy the top, multiply by the bottom flipped over. Sine times sine, the divide by 1 doesn't do anything, so we get rid of it. Sine squared plus cosine squared. This here, by the Pythagorean identity, equals 1. Let's label where we use those reciprocal identities. Awesome. Okay. Express the first trigonometric function in terms of the second. This is pretty quick, especially if you use that chart I did at the very beginning. Cosecant in terms of sine is just 1 over sine. That's 35. 36. Cotangent is equal to 1 over tangent. That's a reciprocal identity. 37. Secant is just 1 over cosine. Cosine in terms of sine, though. Ooh, this is a tricky one. So, cosine in terms of sine. Here's what we're going to have to do. We're going to have to first use, oh man, yeah, so this is a real tricky one. I'll show you how to do it though. So cosine in terms of sine. The identity that relates cosine and sine is the Pythagorean identity. So what we have to do is start with the Pythagorean identity and isolate cosine, and it will be in terms of sine. I'm not expecting you to be able to do this on the quiz. Maybe a good bonus question. And now when we take the square root of both sides, we'll get that cosine is equal to the square root of 1 minus sine squared. Here we have expressed cosine in terms of sine. That is a tricky one. All right, number 39, very last problem. We'll do it for you here. Thanks for sticking with me this long. Which side of the equation below should you transform to verify the identity? Cosine squared plus tangent squared minus 1 equals sine squared. This is equal to tangent squared. To verify the identity, well, there's a bit of a rule in trig verifications that it's easier to simplify than it is to build up. So it's easier to simplify than build up. So we should simplify the left. Therefore, simplify the left. Now you could also say, well, maybe we should do both sides and kind of meet in the middle. That's also a decent idea. Let's actually go ahead and solve this one. This will be a good one. Cosine squared plus, I'm going to use a quotient identity to make this. Sine squared over cosine squared minus 1 all over sine squared. That was a quotient identity there. Now I got to get them to have a common denominator on the top. So that means multiplying this one by cosine squared over cosine squared, making it cosine to the 4th over cosine squared plus sine squared over cosine squared minus cosine squared over cosine squared all over sine squared. Still all equals tangent squared. Now that I've got a common denominator, I can combine the tops. This is going to be cosine to the 4th plus sine squared minus cosine squared all over, well, 1 second, all over cosine squared. And all of that is over sine squared. Copy dot flop. I'm going to copy the top here. Cosine to the 4th plus sine squared minus cosine squared all over cosine squared times. I have to flip this over, which would make it a 1 over sine squared equals tangent squared. All right. What do I want to do here? Bring in the sine squared on the bottom. And then I'm going to want to factor out, yep, okay. So cosine to the 4th plus sine squared minus cosine squared all over, I'll do it in this order, sine squared cosine squared equals tangent squared. I'm going to want to factor out a Pythagorean form here from the top. Is that what I want to do? I could distribute. Oh, okay. Yeah. this is for these long ones, I mean, it's just trying stuff out. So what I'm going to try is just distributing that division to all of the terms, because I see that a lot of stuff will be able to cancel if I do that. There was probably a smarter way to do this, I'll admit it. But it's hard to see the forest through the trees sometimes. You just got to try things. All right, two of these can cancel with that. This can cancel with that. This will cancel with that. Now what do I have? I've got cosine squared over sine squared plus 1 over cosine squared minus 1 over sine squared. I think I made that easier. I mean, that's a cotangent squared. And this, I need to, if I can get this to look like secant squared minus 1, then I'll be in good shape. Let's try combining these two now, but not that one. I don't know, maybe I'll make this a cotangent squared for a second. Sine over cosine sine minus cosine over sine cosine. Those are squareds. Oh, I'm getting there. Oh, man. There was definitely an easier way to do this from the start, I think. I'm seeing some other ways. Because I could have swapped out the cosine squared minus 1 for a sine squared. You know, honestly, when you get stuck, you got to go back to the top. I know I've probably lost most of you. Let me retry this one from the top. Okay. Cosine squared plus tangent squared minus 1. All over sine squared. Oh, I think I can see it now. This here, if I take my Pythagorean identity, sine squared plus cosine squared equals 1, and I subtract 1 from both sides and subtract sine squared from both sides, I'll get cosine squared minus 1 equals sine negative sine squared. So this plus this can become a negative sine squared. All right, so now I've got a negative sine squared plus tangent squared all over sine squared equals tangent squared. I think this is going to work out a little bit better. That tangent, I do want to rewrite it as, here, I'll just save space here. A sine squared over cosine squared, so that I can factor out a sine squared, leaving behind. So a sine squared, leaving behind a negative 1 plus 1 over cosine squared, all over sine squared equals tangent squared. These will cancel. Now I've got a negative 1 plus, that's the same as secant squared equals tangent squared. And that, if I take tangent squared plus 1 equals secant squared, and I subtract 1 from both sides, I'll have tangent squared equals negative 1 plus secant squared. I can sub that in there. Now I've got tangent squared equals tangent squared. All right, thanks for sticking with me. Sorry that this one didn't work out. I mean, I'm sure there was a way to make it work out, but this was the much quicker way. And we verified it. All right, if you stuck with me to the end, good job. That is the end of this one.